So, today in this session we are going to learn about transistors. So, they are the basic building block like PN junction in electronics communication. So, here transistors will be are of two types. One is BJT and the other is FET. So, this is not in our syllabus, you will learn this in engineering. So, here what we have to learn is BJT, that is bipolar junction transistor, in short BJT. This is field effect transistor, that is not in our syllabus. So, we are going to learn about only BJT, that is bipolar junction transistor. So, transistor word, transistor is transresistor, is the contraction form of transresistor. So, the word transistor has originated from transistor. So, this is the, we have contracted, taken out this RE, so transistor. So, this is the contracted form of transresistor, that is the transfer of resistance, or some we will talk about later why it is transfer of something resistance, transistor. So, we are interested in here transistor, that is bipolar junction transistor. In transistor there are three terminals. A transistor has a three sections, one in which there is two types of semiconductor, P type, and in the middle section this is N type, and there is one other type of transistor possible in which this is N and this is P and this is N. So, you see here this is a block representation of a transistor. So, in a transistor we have a crystal in which there are three sides, three sections are there, one this side, another this side, and in the section which is sandwiched between the two sides is called base. This is called base and we call this as emitter and this is collector. Here also this will be called base. So, the sandwich section will be called base and the side sections, one will be emitter, one will be the collector. So, transistors we will be calling at BJT or bipolar junction transistor has three sections. The section which is sandwiched between the side sections is called base and other sections are called emitter and collector. They will be of two types, PNP type and NPN type. So, let us see why we call them there are three terminals connected to this. So, let us see the nomenclature of these terminals, their symbols, their representations first. Now, let us come to the different types of BJTs and their representations. So, we have a block representation of this transistor. This is base. Let this, suppose this is PNP type, this terminal will be called base and this will be emitter, this terminal is called emitter and this terminal is called collector. We had a symbol for this, the symbol for this is this is base, short name, this is emitter and this is collector. If it is PNP type, then we have an arrow like this. This arrow tells the direction of the current, we will see later on. So, this is the symbol of a PNP transistor with these three terminals, this is emitter, collector and base. Similarly, we can have NPN. This is your base B. Now, I will write simply base by B, emitter, and this is the collector. The symbol for this we are going to use is same like this. This is the base, this is collector, and this is NPN. So, this is the symbol for this NPN transistor. This is the symbol. You see this arrow. So, this is NPN, this is PNP, and this is NPN. So, these are the symbols. Now, let us see that how to determine and what is the difference between this emitter and collector, this section and this. This is P side, this is P side. So, why we call them base, what is emitter, what is collector, what is their doping levels, and this and that. In a transistor there are three sections. The sandwich sections, the sandwich section is called base, and the other side sections are called emitter and collector. So, its nomenclature is emitter and collector. The emitter is highly doped and is the source of external charge carriers. So, that is why it is called emitter. The base is small, and thin and is lightly doped. The collector is largest in size and moderately doped. So, if we want to determine or discuss the size of their size, so you just see this is suppose P type, this is N type, and this is P type. So, you see this base is thin, this is base, this is emitter, and this is collector. So, this is highly doped, this is lightly doped, and this is moderately doped. So, this is the doping level. So, you see here, let us summarize the construction of a transistor. In a transistor, N type is sandwiched between two P types, or P type is sandwiched between two N types. So, thus there are two types of transistors, PNP type or NPN type. The base is thin and the lightly doped. This collector is moderately doped and comparatively large in size, and emitter is this highly doped and moderate in size. This is the constructional details, and you see we do not have a crystal like this. The actual transistor will be different. This is just a block representation of this transistor. schematic representation. Let us see the actual transistor. Please copy it. So, now let us see, this is the actual transistor crystal. So, you see what we do, initially we take this whole block of a transistor, this is the whole block of a transistor, and then we make this side only P. So, we diffuse this side with and make it P type. So, you see we make this P type, the whole P type, and then this side is made N type and this is P type. So, you see this base is this here, base, this is the base. You see this base seems to be larger than P, this is correct, this base is larger, but here I have shown this. So, here I mean that this I am representing this a block diagram. So, when I say this is thin, that means the distance between these two junctions is thin. So, that means the distance between these two junctions means this is the junction, that is emitter, base, and this. So, this distance is small. So, this is thin means the two junctions are very close to each other. So, you see here this size of N here is more than P, but we are not related with the size, we talk about this, the distance between the junctions. So, when I represent by a block diagram, this size means the distance between the junctions. So, this terminal is called emitter and this will be called base. So, here you see this is a metallic contact directly connected to P, this is a insulating medium, and there is a metallic contact here that is soldered to this N type, this is base, and this whole P type is soldered here with a metallic contact, this becomes the collector. So, this is actually a transistor that is shown in a block diagram, the schematic diagram is this. So, this is a complicated diagram, we can't use in circuits. So, we use this type of diagram to represent this transistor. Now, you may think that transistor is nothing but a PN junction. This is P type, N type junction, and there is again a N type junction and a P type junction. This is PN junction connected back to back. It is, of course, it is a two PN junctions connected back to back, but this time these two junctions are called interacting PN junctions. Thus a transistor is a two PN junctions connected back to back in which the junctions interact. So, very important point, it is the interaction of junctions which makes the working of a transistor. So, let us see. Now, this is a transistor, and we see that here we have the base, this is the base, and this is the emitter, and this is the collector. So, what happens? This doping level of, suppose this is P type and N type, this doping level is very high. So, what happens? A depletion layer is formed. So, a depletion layer is formed here, and this depletion layer, this is PN type, has a potential barrier like this. Again, there is one more junction here, PN junction, this is P type, and this is N type. Then here also a potential barrier is formed. This potential barrier is here positive and here this negative type. So, you see here the electric field due to this is here, potential barrier, and this is like this. These are the potential barriers. Now, since the doping level is high, so the depletion layer, let us not compare depletion layer now. So, now let us see what happens. Now, if this is a transistor, a normal transistor, but suppose if we have a PN junction, this is P type and N type, and there is another PN junction, so that this is P type and N type, and just we have connected it. If we have just connected it, then this is different completely from this different. Although this whole side is N type, this is P type and P type, this will not act as a transistor. So, in this back to back two PN junctions, the junctions, you see this junction, this is called J1 and this junction is called J2, are far apart, so they do not interact. So, in a transistor, the base is made thin, so that the two junctions, one is emitter base and the other collector base, are so close that they interact and cause transistor to work. That is called transistor action. So, that is why we want my base to be thin. That means, now we have explained the constructional details of a transistor, that emitter should be highly doped, this is moderately doped, and this should be thin. Why this is thin? Because if it is thin, then these two junctions can interact and so transistor can act. Otherwise, if it is thick, then it is just two PN junction connected back to back, which will not act as a transistor. So, for transistor it is required that the middle region base should be as thin as possible. Next, let us see what is transistor action. Now, let us discuss about transistor action. So, let us draw some exaggerated diagram of this transistor. This is my transistor. Let us talk, this is P, this base is from here to here, I am showing this base, this is N type and this is P type. Now, let us earthed, this P type also earthed. So, in a transistor, this is an exaggerated block diagram. We are not interested in showing the constructional details. What happens when you earth it? Then here the depletion layer is formed like this. Depletion layer will be like this. The depletion layer is, suppose I shade my depletion layer for this like this. This is the junction which is between emitter and base, and here also the depletion layer will be like this. I have shaded in this direction. this is the depletion layer and this is my base. This is N type. So, this is the depletion layer of this and this side depletion layer of this. You see this potential barrier here, the potential barrier will be nearly the same for these two. So, they will be like this. Now, suppose I connect these junctions for transistor action, what happens? Let us see. You see, this is the base region, that is N type, this is P type, this is again P type. Now, let us see how it has to be connected. This is the PN junction, we always connect it for transistor action, it should be forward biased. So, P should be connected to the positive terminal, N should be connected to the negative terminal. So, this junction becomes forward biased. I have to make this junction reverse bias. So, I will connect this P type with the negative terminal, then N type to the positive terminal. So, this becomes reverse bias and this becomes forward biased. This is P is connected to positive terminal, N is connected to here negative. So, this is forward biased and here this junction P is connected to the negative, N is connected to the positive. So, it becomes reversed bias. Now, due to forward biasing, you see the depletion layer is here decreased. Depletion layer is decreased. So, you see this depletion layer is decreased. Here it was this much, now it is decreased. Here suppose it is the width of depletion layers is very less, of the order of micrometers. So, this layer has been decreased, whereas due to this forward biasing, reverse biasing, this width has increased. So, previously it was this, now you see it has increased to this portion. So, it has increased. So, previously this was the depletion layer, now it is here and here it was like this. So, here depletion layer has increased. So, here depletion layer here, depletion layer increases due to reverse biasing. And here this depletion layer decreases due to forward biasing. So, what is important is that initially there was a width L. This side, the right side of this depletion layer and the left side of this depletion layer. So, the distance between them was L. Once we bias this, you see this has come down this. Now, we keep this biasing more. You see, I have given suppose a single cell here, double cell. So, this reverse biasing is more. Why reverse biasing is more? Because if we reverse bias more, then you see what will happen, this depletion layer will penetrate this side more than how much it has contracted. So, this becomes L dash less than L. That means, this width here, this region is with proper biasing, this is narrowed down. So, the narrowing of this region due to the penetration of depletion layer into the base region is the basic cause of the transistor action. So, you see again what happened. When I bias it, then this junctions, one junction gets contracted, but one is increased. So, as a result, overall distance between these two junctions got decreased as a result they may begin to interact. We will see now how they will interact. So, very important point about the depletion layer at the two junctions. So, due to biasing we are able to make this depletion layer come close to each other. The penetration of depletion layer increases into the base. This is what we do when we bias a transistor. You recall the fundamental process in a PN junction, when we bias, then we change the diffusion current and the drift current. That equilibrium is disturbed. When we bias it, we make these depletion layers interact with each other. So, in transistor, how the two PN junctions interact, that is what we have to study. That means how the depletion layer interact with each other. So, now we are talking about the transistor action, and we have seen that due to biasing this junction, this depletion layer is thin and this is thick. Now, let us first remove this biasing. Let us see back to when they are earthed, when they are connected or they are earthed. Suppose I earth it all this, so or we are connected it. So, you see the depletion layer, now I am concentrating more on depletion layer. So, I said that this depletion layer will be something like this. This depletion layer is like this. So, this was the depletion layer. We talked about this, that due to biasing this is going to, this distance, this L distance is going to decrease. Let us concentrate more here. Now, this time I am talking about the biasing level, the doping levels. So, you see this is the base region and this is the emitter region, which is P type, and this is N type. So, now we know that this is highly doped and this is lightly doped. So, what happens if the doping levels are equal in these two, then this junction here, this width and this width and this width will be same if the doping level is same. But actually the doping level of emitter is very large. So, doping level is very large. So, what happens? The doping level is very large. So, this side, this will be, you see, this is the metallurgical junction. Metallurgical means the contact between P and N type. So, this junction width, this side is less compared to this, because here doping is high. So, the region where doping is high, the width of this depletion layer will be less. So, so you see here, now the width is like this. So, the doping of this emitter should be very large compared to this base region, so that the depletion layer will penetrate more this side. Now, what about the doping level of this? This is lightly doped, this is lightly doped, and this is moderately doped. So, what happens? The doping level is here more. So, you see here this depletion layer is something like this. So, you see this is the depletion layer. So, please concentrate here. Since this is lightly doped and moderately doped, its doping level is more. So, this will be more than this factor. So, you see here. So, the doping level is such that this base region is lightly doped. So, these junctions will be very close to each other. So, that is why we keep such doping level. So, what we want? So, my doping level and this base width is designed in such a way, so that the two junctions, the depletion layers are as close as possible. So, this is the effect of doping level on the depletion layer. Now, come back to the biasing, that is when we bias it, then what happens to the depletion layer and how the two junctions interact, and in their interaction causes the transistor action. So, now this is the PNP bipolar junction transistor which is biased. So, the transistor when put in active mode, i.e. the emitter base junction is made forward biased, and collector base junction reverse biased. Active mode means, with active mode we mean that the emitter base junction is for the transistor when put in active mode, i.e. emitter base junction made forward biased and common collector base junction reverse biased. This is what active mode is. Now, the depletion layer at emitter base gets reduced and at the collector base gets enlarged. As a result, they penetrates more in the base regions. So, what happens? You see this barrier is reduced. So, this depletion layer is reduced and here it is increased. Now, the barrier field is here positive negative type, and here you see this, here it is positive and this is reverse bias. So, the field here is in this direction, this is large and this field is less. So, due to forward bias the net field is, electric field is here less and here large. So, now let us begin that during transistor action how current begins. So, you see here the positive polarity of this forward bias, that is the positive polarity established here, pushes these holes towards the junction. These holes are in majority of charge carriers in the p type, they are pushed towards this barrier. Now, here this barrier has a order of 0.7 volts for silicon and for germanium it is 0.3. So, these holes are able to migrate, diffuse towards this junction and they reach here, So, they reach here. Now, in this N type base which is lightly doped, some of these holes may combine with electrons, So, this electron is lost here, you see. So, the holes when move they constitute a current that is called I emitter. So, some holes go this way. So, the motion of these holes constitute a emitter current. Now, some of the holes which is still migrating, and so you see here some of the holes which has combined with the electrons present at the base, So these electrons are robbed out. So what happens? We say that there is a IB current. So those electrons which combine with holes here constitute hole current IB. Now what happens to the remaining holes? So since this depletion layer has penetrated, this length is so much decreased by this biasing that these holes manages to reach here. Since this medium is thin, so once they manages to come on their own up to here, from here to here they manage to come, then you see there is a field here, that is field due to this reverse biasing, that electric field swaps this and so they finally reach and are collected at the collector. So these holes automatically comes here by diffusion. So once they reach here, the electric field here due to this reverse bias automatically swaps them, collects them, and so we call this collector. So why its name is collector? Because at this end, due to this reverse bias potential, we are collecting the holes and the holes float up in this collector region. Why its name emitter? Because they are emitting, they are providing the positive charge carriers holes if it is PNP type. If it is NPN type, then these will be the electrons. So you see the depletion layer gets reduced and this. So the positive potential of the forward bias pushes the holes which are majority charge carriers towards the emitter base junction. So this positive potential pushes these holes towards this. The diffusion of these holes towards the junction causes emitter current. Let us call it IE. Just take down this. Since the holes are emitted by the P side, so that side is called emitter. So emitter name, the origin of the name emitter is because it emits, it is the provider of the holes. The holes diffuse to the N side, that is base, where majority of them pass to the collector region. Since the base is thin and the depletion layer is has penetrated large in the base region. However, some of the holes in the base region combine with the free electrons of the base to constitute a base current. To constitute a base current. You see, very few electrons, holes will combine with the electrons because the base is lightly doped. Since the base is lightly doped, so only a few percent of holes will combine with the base electrons. The majority of holes when reaches the collector base depletion layer is collected by the collector base voltage, and so they constitute collector current. Since the collector collects the holes, so its name is collector. So, why its name is collector? Because it collects. The holes float up in the collector. So, thus you see here only few percent of these holes has reached here. So, we say that the total emitter current will be the sum of the base current and the collector current, if I assume that this current is due to the majority charge carriers. Since majority charge carriers are the cause of major currents, so we say I is equal to IB plus IC also we can say. So, this is how current conduction in a transistor when it is under active mode is done with the help of holes. Active mode means PN junction, this emitter base junction is forward biased and collector base junction is reverse biased. This is what we mean by active mode. Now, you see, I said that it is interacting PN junction. Now, suppose it is just a two PN junction connected back to back, what will happen? Then the holes coming from this P side will here meet with the electrons from N side, and so they won't come to this collector region and won't be collected. So, there won't be any transistor action. So, then what will happen? Then this IE, thus these holes will meet these electrons will become equal to IP. So, then IE won't be equal to IC and all the holes won't pass through this region. So, what is important is that these two portions, the depletion layer should be so much narrowed that most of the holes should come from this side to that side. So we can say that these two junctions are interacting. That means my base should be thin and should be lightly doped. This is what transistor action is. So, now let us see transistor currents. So, this is a PNP transistor. Let us see the biasing, that is in the active mode. When transistor action is this is forward bias. So, P should be connected to positive terminal and N should be connected to the negative terminal. We say this is VEB, that is emitter base bias. Now, this should be reversed bias. So, reversed bias means P should be connected to N side negative terminal and this N side should be connected to positive terminal. This is V, this is collector base VCB. This is VCB is this bias, reverse bias, and this is. Now, the current, this is emitter current. So, this current is because these holes are moving like this. So, if I denote this current like this by an arrow, you see this current is represented by this arrow. Then what happens? Some of this current passes here, some of this current passes to this is the base region to form IB, this is IE, and rest of these holes will migrate towards this to form IC. So, you see this diagram tells that some current drains out to IB, that is generally 5%. So, we say I emitter is equal to I base plus IC. So, since IB is small, nearly 5%. So, if that error can be neglected, so IC is of the same order, but somewhat lesser than IE. So, IC is of the same order of this emitter current, but lesser than this. This is how the current nomenclature of currents. So, the holes here, when they reach here, they meet with these electrons, and so the motion of electrons is here. So, I say the current is hole IC, and you see these holes are here, these holes meet with the electrons from n type. So, electrons are robbed, so positive charges will come, that is we will say that the current flows along this direction IB. So, you see IE is equal to this relation. Now, in transistor action, we define a quantity called current amplification factor, current amplification factor, current amplification factor alpha. It is defined as the ratio of the collector current to the emitter current at constant, this by this ratio at constant collector base VCB. So, we define this alpha as IC by IE at constant VCB. Now, since here we have applied DC voltage, so we sometimes write this as alpha DC. Alpha DC is IC by IE by VCB, is also called DC current gain. DC current gain. You see alpha is less than 1. So, alpha, you see this IE is always greater than this. So, alpha is less than 1. Now, base current amplification factor, we call this beta, and since you see DC voltages are applied, so we will call it beta DC or simply beta presently now. Now, we define it as, it is defined as the ratio of the collector current to the base current when VEB, emitter base voltage, is constant. So, we call this as beta, and let us call it beta DC is equal to IC by IB at constant EB. So, you see here this quantity is greater than 1. So, beta is greater than 1. So, this is how we define beta. So, now I will find out the relation between alpha and beta. Please copy it first. So, now relation between alpha and beta. Let us relate alpha and beta. So, you see alpha already I have defined as IC by IE and beta as we have defined as IC by IB. This is already defined. So, now we know that I emitter is equal to I base plus I collector. So, let us use this relation. I emitter becomes I collector by alpha, I base as I base as IC by beta plus IC. So, you see here IC can be IC is here IC is correct, IB as replaced by IC by beta. So, IC cancels. So, 1 by alpha as 1 by beta plus 1. So, 1 by alpha is equal to here 1 plus beta by beta implies alpha is equal to beta by 1 plus beta. This is how alpha and beta is related. Now, we can also relate this alpha and beta. If you want to relate with beta and alpha, then we can here only from here we start. Beta means 1 by alpha minus 1 is 1 by beta. So, 1 minus alpha by alpha is equal to 1 by beta implies beta is equal to alpha, beta is equal to alpha by 1 minus alpha. So, either alpha can be written in terms of beta or beta can be written in terms of alpha. This is how alpha and beta are related. So, now we have completed our transistor action, how transistor action takes place and how to relate these currents alpha and beta, IE, IB and IC. So, next topic we are going to see is the transistor biasing and characteristics of a transistor in different modes.